Okay, so today we're going to cover chapter 6 in more detail, do some things that I had done in the video, continue with that subject. We're going to basically cover everything in chapter 6 today. So after this, we'll hopefully be doing the lab. Connie, was Heaven on the bus? Did you come on the Green Country bus?
Yeah.
Was Heaven on it? Okay. All right, so let's talk about conservation of energy. So we were looking at something going down an incline, and what we did was we, at the top, the middle, and the bottom, we did mechanical energy, kinetic energy, and potential energy. The first time it started from rest, and the second time it was pushed. In each case, your mechanical energy is the sum of your kinetic plus your potential. And then we solved our kinetic energy by getting the difference between the mechanical energy and the potential energy. So we went through a problem, and then we did it again where we pushed. Now, keep in mind, the potential energy is independent of whether you push. It's just related to the height. Friction does not change your potential energy. Okay, the kinetic energy is the mechanical energy minus the potential energy. So if you push at the top, you add to that mechanical energy, that changes your kinetic energy. All right, potential energy at the bottom is 0, always. And the mechanical energy at the bottom is equal to the kinetic energy at the bottom, and that is always true. Now, what happens when we add friction? Okay, what is friction going to affect? Right? Which affects what as far as energy? Kinetic energy. It's not going to change your potential energy. It's going to change your kinetic energy and therefore your mechanical energy. So we're going to repeat the same problem that you've done twice now. We started out where we had a 2 kilogram mass. It was 20 meters up. So you should have it in your notes, 20 meters up. And we first did it at rest, and then we pushed it at 3 meters per second. So just open your notes to that page where we had started it. So first we did it from rest, and then we pushed it at 3 meters per second. And we're going to continue that same exact problem. Okay. So this time we're going to lose 30 joules in the first half and 30 joules in the second half. You're going to repeat the same problem, telling me the mechanical energy, the kinetic energy, the potential energy, the speed. It is again pushed. Okay, so just like before, it's pushed. The same speed, same ball, not a ball, we'll call it a
sled.
What?
You said a sled?
Yeah, we can call it a sled. So it loses 30 joules in the first half and 30 joules in the second half to work done by friction. Okay, so I want you to recalculate your 3 things at the top, the middle, and the bottom.
Was it where the height was 10 meters? Was it that one?
No, it was this one. The height was 20 meters. In the middle, it was 10 meters. You might be looking at the middle. This is the only one we did. I know you were here.
Yeah, I know I did. I just can't find it.
So it was a 2 kilogram mass, 20 meters up. Okay, so you're looking at the same thing. Samuel, can I use your phone charger to check my calculator? Maybe not your phone charger, your calculator charger.
I might have to go back and read it.
I'm gonna try to multi-compensate that, find it. Here. Oh, well, maybe tomorrow. Thanks anyway.
I'm gonna read it wrong. Nothing. Nothing.
Okay,
I can bring it Thursday.
okay, thank you.
So would this be, basically, the total would just be minus, it'd be.
The total mechanical is kinetic plus potential. So it's the same problem you did before, same problem you did last time. It's pushed at 3 meters per second to a kilogram mass. But this time you're losing in the first half to friction and you're losing in the second half to friction.
Okay.
Okay, so what we're doing now, we're doing the mechanical energy called MU. Let's see what's this one, the kinetic energy plus potential energy. We're at an incline, so we missed classes we went to the previous part. It's 20 meters on 2 kilogram mass is pushed at 3 meters per second. Kinetic energy is only have one square. Potential energy is mgh. So the kinetic energy is equal to 1/2 to 10 times the square. Potential energy is 4 meters. That's 1 feet. That's a 2 kilogram mass. Okay, so then I have them at the top. And so there's the mechanical in the middle. And the middle potential energy is 1/2 as much. What it is at the top. And then at the bottom, the potential energy is equal to 0. And the mechanical energy is equal to the kinetic energy. Alright, so I also on this problem when I use friction. 30 joules and 30 joules is lost from the mechanical. So you have to sum these two together to get your mechanical. Then let's subtract 30, so we build up to this problem over 20 if you watch the videos noticing. So just get your mechanical energy here. Sum these together. Neither one of my calculators is working. To have a calculator of any kind. Does anyone have an extra calculator? So your kinetic energy at the top is the same. The friction doesn't affect anything at the top. Potential energy at the top is the same. Your mechanical energy at the top is the same. That's what you already got. After that, right, your numbers change. So we still have 392 for our potential energy, your kinetic energy from the push of 3 meters per second, right? That gives you 9. Is it this one. So you still have 401 as your mechanical energy at the top. So you have 1/2 2 times 3 squared is 9 joules. That's your kinetic energy at the top. Potential energy at the top is still 392. 2 times 9.8 times 20. You sum those together, you get 401 joules.
Wait, so is 9 the push?
9 joules comes from the push. That's the kinetic energy from the push. 1/2 m times v squared. And then the potential energy was the 2 times 9. That is the same thing as the last problem. It's exactly the same. The friction only affects after the high point, right? Because when you're starting out, that doesn't matter.
So with the potential energy, does it affect potential energy?
No, it doesn't change anything in potential energy friction. So your potential energy is the same as previous problems.
So 1/2 mv squared is to calculate the initial velocity.
Your kinetic energy, your initial kinetic energy. Okay, so you get your potential energy in the middle. Once you have your potential energy in the middle, you can get your kinetic energy in the middle, but you have to also subtract that 30 joules. What do you do with that 30 joules? 30 joules lost to friction. What do you do with that?
Subtracted
From what?
by that 9 joules.
Which is called
Probably.
mechanical energy. You're subtracting that from your mechanical energy. Okay, 30 joules is lost to your mechanical energy in the middle, so that gives you, you're no longer keeping the same mechanical energy throughout. And then you use 30 joules again in the bottom. That affects your speed. Your speed should be different from before. You're going to get your speed in the middle and your speed at the bottom.
Potential energy at the bottom. So we are in which is number 2.
It's not that hard once you get used to it.
Because you have more.
Oh.
It's because we left off on 2 and are picking up now that it seems harder. So our kinetic energy was 401, the same as before. We have to subtract 30 joules from that to get our mechanical energy in the middle. Okay, because we're losing 30 joules in the first half and 30 joules in the second half. So we start out, we have the same thing. Potential energy is the same. Kinetic energy is the same. Mechanical energy is 401 joules. We just went mgh, 1/2 mv squared. We added these two together. Now we subtract 30 joules to get the mechanical energy in the middle. So what's the mechanical energy in the middle? Joyce? What's 401 minus 30? So we have 371 joules in the middle is our mechanical energy. Now, our potential energy is the exact same thing as before. It is 1/2 our potential energy at the top. It is mg times 10 meters. So how are you going to get your kinetic energy in the middle?
49.
For your kinetic energy?
Yeah.
How'd you get that?
I did 196 equals 2 e squared.
Potential energy isn't equal to kinetic energy in the middle.
Oh.
Mechanical energy minus the potential.
Right. You have to take your mechanical energy, subtract the potential energy to get your kinetic energy. We said all along that your kinetic plus your potential is equal to your mechanical. I have it right here. Your mechanical is the sum of the two. So if you're looking for kinetic, you subtract the potential from the mechanical. So what's the kinetic energy in the middle? Violet, do you have it?
I got 175.
Good. So all we did was go 371 mechanical energy. So write it down if you didn't get it. Mechanical energy minus potential energy is equal to kinetic energy. So 371 minus 196 is equal to 175, which is equal to the kinetic energy. So then from there you get your speed, because you know that your kinetic energy is equal to 1/2 the mass times v squared. So you solve for your speed in the middle. After that, you get your potential energy at the bottom, your kinetic energy at the bottom, your mechanical energy at the bottom. So what's the speed in the middle?
13.2.
Good. So we had a 1/2 and a 2 here. We cancel that. So we take the square root of 175. The square root of 175 is 13.2. That's your speed in the middle. Now do everything at the bottom. So what's the mechanical energy at the bottom? Connor?
I don't have it yet. Well, it should be the same. I mean, um, like 341.
Right, you're just subtracting 30. It's 341. What's the potential energy at the bottom? 0. So what's your kinetic energy at the bottom? 341, right. We lost to friction 30 joules, so we're at 341 now for our mechanical energy, which is the same thing as our kinetic energy. At the bottom, your mechanical energy and your kinetic energy are the same. You plug in and you solve for your V at the bottom. Your potential energy at the bottom is 0. Lincoln, what's the speed at the bottom?
I have 18.46 meters per second.
Good. We just set that equal to kinetic energy and solve. So I think you just need to write it down if you haven't already. Let's go through it right here. Okay, so you're going to write it down if you don't have this. Mechanical energy at the top is the kinetic energy at the top plus the potential energy at the top. If there's friction, you subtract out this work done by friction from your mechanical energy. So the mechanical energy in the middle is equal to the mechanical energy at the top minus the work done by friction. So write this down. Can you understand, Connie?
Well, what did you say? Could you say that?
Mechanical energy at the top, this T is for top, is equal to kinetic energy at the top plus potential energy at the top. Then if there's friction, your mechanical energy in the middle is equal to the mechanical energy at the top minus the work done by friction. The kinetic energy in the middle is equal to the mechanical energy in the middle minus the potential energy in the middle.
What's a W?
Work.
Oh,
Now, if there's work lost to friction again, the mechanical energy at the bottom is the mechanical energy in the middle minus the work done by friction. The work done by friction is subtracted from your mechanical energy. So you're starting out with energy, just like in the lab. If you have friction on the pivot, you're losing energy. The kinetic energy at the bottom is equal to the potential energy at the bottom. Kinetic energy at the bottom is equal to the mechanical energy at the bottom. And the potential energy at the bottom is always 0. Potential energy is never influenced by a push or by friction. It is only determined by FGH. It's strictly related to the height. The kinetic energy and the mechanical energy are affected by whether you push something or whether or not there's work done by friction. Did you write everything down? Do you understand? So you have this energy that comes from the height. The higher you raise something, right, the faster it's going to hit the ground. It comes from the height you've raised it and whether or not you've given it a push. That energy, which is 100, let's say it starts from rest, that energy, which is 100% potential, becomes 100% kinetic at the bottom. If you give it a push, you have both kinetic and potential at the top, but it's still only kinetic at the bottom. Because that is an outside force acting when you give it a push. if we have friction, right, that's going into thermal energy, it's going into heat. It is being lost to heat. So our energy is becoming less. We're subtracting that from our mechanical energy. Our kinetic energy is the mechanical minus the potential. So whatever we have left for speed comes from what did we start with and what goes into the height. So we spoke about the kids pushing on this wing. They stick their legs out, it creates kinetic energy, potential energy. They pull their legs in. They're creating kinetic energy by pulling their legs in and dropping the potential energy to add energy to that system. So even though there's friction in the pivot and air resistance, they can go on forever if they're big enough to push their legs. Okay? All right, let's do one where we start from scratch. A 70 kilogram mass, its speed is pushed at 4 meters per second. It is an incline 30 meters up. There's 1,200 joules lost to friction in the first half, 1,100 joules lost to friction in the second half. I want to know the whole thing at the top, the middle, the bottom. This is a summary of like everything we're doing in this chapter of, except for the work kinetic energy theorem, it really summarizes the chapter.
So it's like 1,200 joules of,
Work that lost to friction in the first half and 1,100 in the second.
It's let go at 4, so that's our kinetic energy at that point. This is the changing kinetic energy. We're starting from this. So our kinetic energy is 1/2.
So our kinetic energy is 1/2 70 times 4 squared. Our potential energy is 70 times 9.8 times 30.
Just add those two together to get your kinetic energy at the top. There was no question, just a zero would be variation.
So you get 560 and 2,000 and 580 joules. You add those two together to get your mechanical energy at the top, which is 21,140 joules. Did you get that?
So potential energy in the middle is half of it. So it's just because you're halfway. Potential energy is in GH, where H is half. So that's why it's half. And then mechanical energy in the middle, you have to subtract half of it by friction. So we take our mechanical energy in. Subtract 20 joules from friction. Kinetic energy in the middle is going to be mechanical energy minus the potential energy. Top minus. So your mechanical energy in the middle is mechanical energy right there minus the friction.
So our mechanical energy in the middle is the mechanical energy at the top minus the work done by friction. You're getting your speed in the middle and your speed at the bottom. We know our potential energy in the middle is half the potential energy at the top. Okay, so your potential energy in the middle is 1,290 joules. Because it's half what it is at the top. The mechanical energy in the middle, we subtract out the 1,200, you get 19,940 joules. Okay, that's your mechanical energy in the middle. Now you can get your kinetic energy in the middle because it's the mechanical energy minus your potential energy.
And it's negative, does that just mean it's?
Shouldn't be negative. You go I think maybe you did potential minus mechanical. It should be mechanical minus potential. So that would be 19,940 minus 10,290. That's a positive number. Samuel, do you have the kinetic energy in the middle?
Yeah, I have 9,650 joules.
Good. So we subtract what we got for our potential from our mechanical to get 9,650 joules.
I gotta do the potential energy.
What'd you get for your potential energy?
I did 70 times 9.8 times 200 in that copy. 20,530.
If you're gonna go halfway up, you would go 70 times 15 times 9.8, right? Because halfway up, your height is 15.
Mm-hmm.
Now you get your speed in the middle. And then you do the same thing at the bottom and get your speed at the bottom. We're just going to keep hitting these problems until you get it. After a while, it's a routine. Show me if you're done. It's all for you. Yeah, it's not right for the speed in the middle. You said it equal to 9650. 70. Just checking that. Okay, so now we set this equal to 100 and speed in the middle. So we have 96,000 squared. Divide both sides by 35 is 5 into the square. You get it?
That's like the look. Essentially kinetic.
Did you get your mechanical energy in the middle right corner? 19,940.
And I don't know, I think my calculator messed up. Cause I did the same things y'all did, and it's like, it didn't come out right. Like I did I subtracted 1,200 from the original, and it didn't pop it up right. Maybe I wrote it down. It was way up, there. So I was trying to figure out how to find the speed, you know.
Okay, so we had
I
somewhere.
have to add the one. The 21, wait, is there a
Yeah, you had 21,140 as the initial mechanical energy.
Yeah, I just tried to enter the 1,000, or 21, if I put the 1. I just put a 0.
So what's the speed in the middle? Violet, do you have it?
I got 16.6.
Good. We divide both sides by 35 and take the square root. Okay, 9650 divided by 35 and you take the square root, you should get 16.6. Okay, then at the bottom, what's our potential energy at the bottom? 0.
What's the time we live in? 2030. Okay, still check.
You subtract that from, first, did you subtract 1,200 from 21,000?
No, I got it now. It's just that,
Okay.
that whenever I messed up that one. It completely messed
Okay, now at the bottom, we only have kinetic energy. Our potential energy is 0, right? So you subtract again. What's your kinetic energy at the bottom? Anybody?
18,840.
Right, we subtracted out our work done by friction from what we had for our mechanical energy in the middle, and we get 18,840 for our mechanical energy at the bottom, which is also equal to our kinetic energy at the bottom. You set that equal to 1/2 mv squared. Connie, did you get the speed at the bottom? Good, you should get 23.2 meters per second. We have this 18,840, you set that equal to 1/2 70 v squared. Okay, let's do like, I'm just going to give you some simple numbers and you don't need to use your calculator at all. And we're just going to go through the process. Let's say the kinetic energy, and I'm going to just tell you the numbers. The kinetic energy at the top is 8. The potential energy at the top is 20 joules. The work lost to friction is 2 joules and then 3 joules. I want you to just tell me, go through this same thing. Don't use your calculator. These are simple numbers. Just give me the mechanical, we'll skip speed. Just give me the mechanical energy at the top, the middle, the bottom, potential energy at the top, the middle, the bottom, the kinetic energy, like that.
Is it possible to find the middle potential energy without the height?
Yes. How do you get the middle potential energy without the height? Anybody?
Oh, you do A is equal to PE by mass.
Well, no, there's a real simple way. Can anyone tell me? You have it there in your notes.
Could you solve for the height? Doesn't mean
No, you can't
for
solve
it.
for the height. Look at your notes, see if you can figure it out. Can anyone tell me? How does the potential energy in the middle relate to the potential energy at the top?
Is that half?
It's half.
Oh.
Your half is high up, it's half as much potential energy.
You want speed as well?
Yeah, no, you can't give me that information without math. So what's the mechanical energy at the top?
28.
28 joules. Potential energy in the middle,
10.
10 joules. Mechanical energy in the middle,
26.
26 joules. Kinetic energy in the middle, 16. It's 26 minus 10. Potential energy at the bottom, 0. Mechanical energy at the bottom,
23.
23. We just keep subtracting that. So kinetic energy at the bottom is 23 joules. It's really not that hard, right? Potential energy in the middle is half as much. Mechanical energy in the middle is the mechanical energy at the top minus any work lost to friction. Kinetic energy is the mechanical energy minus the potential energy. Okay, let's do another one. The idea is for you to understand how kinetic energy, potential energy, and mechanical energy are related. Okay, so we have 25 meters up. It's a 10 kilogram mass. It's pushed at 6 meters per second. It loses 200 joules in the first half, 300 joules in the second half. I want to know all the usual things.
Right in the middle, it's losing 200 joules.
In the first half, 200 joules. In the second half, 300 joules. So at the top, you have your mechanical energy is the sum one half 10 6 squared and 10 kilograms times 9.8 times 25. We add those together. Get our mechanical energy at the top. Violet, did you get that?
Mechanical energy at the top,
Yeah.
2,480.
2,630. Your kinetic energy is 1 half 10 times 6 squared. Your potential energy is 10 times 9.8 times 25. So it's 2,630. Now you subtract the work done by friction to get your mechanical energy in the middle.
Okay, now is this number? That was the potential energy on that, and then you had to add in this, which was 180. To get your total sum, mechanical energy being 2,630 joules. The sum of the two. So mechanical energy is this plus that. Where they subtracted 280 from mechanical energy. Okay, now potential energy in the middle is calculated. So if you have 2, 4, 6, add 2 potential.
Okay, so we're subtracting our work done by friction to get our mechanical energy in the middle. Lincoln, what's that going to be?
In the middle, it is 2,630.
That's at the top.
Oh, well, I was looking for 2,430.
Good. We get 2,430 for our mechanical energy in the middle. Potential energy in the middle. Samuel?
I got 1,225.
Right, it's just half what it is at the top. So our kinetic energy in the middle is the mechanical energy in the middle minus the potential energy in the middle. Okay, so we're just taking what we got from mechanical energy in the middle, subtracting out the potential energy in the middle to get the kinetic energy in the middle.
See what the speed in the middle is?
Yes, speed in the middle and at the bottom. Connor, did you get the kinetic energy in the middle?
1200.
Good, so we have 2,430 minus the 1,225. So we get 1,205 joules, and you said that equal to 1/2 mv squared to get your speed in the middle. Okay, so we had 1/2 mv squared, which is 5. Connie, did you get the speed in the middle?
Oh, I got 15.52.
Okay, good. So we're just going, the 1,205 is equal to 1/2 10v squared. So I just did 5. It's 1/2 10. Divide that down, take the square root. Okay, the potential energy at the bottom is what? 0. Mechanical energy at the bottom is,
2,130.
right, we subtract out our work loss to friction. So we have 2,130. We started with 2,430. We subtract 300 to get 2,130 for our mechanical energy at the bottom. Samuel, do you have your speed at the bottom?
I have 20.6.
Right. We set that equal to 1/2 10v squared to get our speed at the bottom, okay? All right, so this kind of summarizes the sum of what mechanical energy is the sum of the kinetic plus the potential. When we have friction, we lose our mechanical energy. The kinetic energy determines the speed, where the more we lose to friction, the more it slows down. Our potential energy is independent of friction. It's determined solely by the height. So our potential energy doesn't change if something is pushed or whether or not there's friction. Okay, now I started in some of the videos the whole work kinetic energy theorem. So let's talk about that. So we spoke about how our work is our change in kinetic energy. So this is used for something moving flat on the ground, because you only have kinetic energy, mainly used in that. It's used in linear and nonlinear situations. So the work kinetic energy theorem is that your work is equal to your change in kinetic energy, which can be written like this, okay? So I went through that with you. We're going to do some of those problems now. Now your work is also equal to your force times your distance for something moving on the ground. So you have those two equations for your work if something's moving on the ground. I went through a problem with you of brake force. Okay, so this is also equal to your force times your distance. So we talked about that too in the videos. Okay, so if I tell you something, a 500 kilogram vehicle applies a brake force of 280 newtons. It stops after how far? So stopping distance. It's moving at 15 meters per second. So you're using this right here, your work kinetic energy theorem, which you just wrote down.
So 280 would be the work force,
That's your brake
or
force.
the brake force?
Yeah. Is that what you just asked me?
I don't really know what I'm asking.
So the vehicle applies a brake force to stop. What's the stopping distance? We did these in the video. Of course, if you didn't watch the video, that's a problem, isn't it? So you have your equation right there for the work kinetic energy theorem. Okay, so the brake force is your force. You're solving for the stopping distance. What's the final speed? 0. So you know the initial speed, you know the final speed, you know the mass. You have everything you need to solve. So you have 1/2 the mass, which is 500 kilograms. V final squared is 0 squared minus V initial squared is equal to your force, 280 newtons, times the distance. Now this is going to be negative. A brake force is a negative, but you get a negative here also, so the two negatives cancel out. You solve for your stopping distance. Violet, did you get the stopping distance?
200.9.
Good. Okay, it's just 250 times 15 squared divided by 280. Now what happens if the speed is doubled?
What was the answer?
200.9 meters. Which is 250 times 15 squared divided by your brake force.
This is a negative.
Oh, wait.
So it would just be 13.
So it would be 200.9, a positive.
Would the newtons change?
No, we're doing the same brake force.
Okay. Right.
Lincoln, what did you get?
I got 803.57.
Okay, good. Now, did you need to go through and recalculate everything?
No, I just really changed the speed and use the same.
But did you need to even change your speed and calculate? What
Oh, yeah,
factor
sure.
is the stopping distance from the original?
The weight, the newtons.
If I double the speed, by what factor does stopping distance increase?
4.
Right, 4 times. Okay, so we have 1/2 mv final squared is equal to our force times our stopping distance after we cancel out the negatives, get rid of the 0. If I double this, remember, when you square the 2, you get 4 times as much. It's 4 times as much. Your stopping distance increases non-linearly as the speed goes up, and linearly as the mass goes up. So if a truck has 20 times the mass of your car, now they have more of a brake force, but it's not going up proportionally, right? They have such a vastly larger stopping distance. And as you increase your speed, your stopping distance, if you double your speed from 35 to 70, your stopping distance has increased fourfold. You should understand that the faster you go, your stopping distance increases non-linearly. And similarly, those trucks have such enormous stopping distance when they have big cargoes. Okay, so let's do another one of these. So in the video, I left off here. So let's say a vehicle is going 8 meters per second, and it increases to 16 meters per second. It's a 400 kilogram vehicle. Tell me the work done. What is the work done for that vehicle?
So you gave us 8 meters a second, 16 meters a second. Is that?
It changes from 8 meters per second. It's moving at 8, changes to 16. What's the work done? The mass is 400 kilograms. Yeah, we're gonna take a break in for like 5 minutes. Is that, can you wait that long?
Yeah.
So 250 times 15 squared, you just square 15.
Oh,
So 16 is pretty close to it because they're both like times.
Let's wear them, but it's like 16 years like something.
We're just using our work kinetic energy theorem. Show me if you have it. So we're going 1/2 400, our final speed squared minus our initial speed squared. Samuel, what did you get?
I got 38,400.
Okay. Actually, I don't know if that's right. Did everyone get that? Okay. Now, I'm giving a brake force of 120 newtons, so tell me the stopping distance. So it's just 1/2 400 times 16 squared minus 8 squared. Just tell me the distance over which this force was applied. So we want to know the stopping distance from 16 meters per second. Okay, so they're at 16. What is the stopping distance?
I'm 320.
So you're going 1/2 400, 16 squared minus 0 squared. Okay, so we're looking
0
at
squared.
stopping distance, right? We're looking at stopping distance. So now you're at 16. And then I want you to tell me, what if the person had only been going 8 meters per second? What's the stopping distance?
What?
Calculated by the dial.
It went from like full charge to just 0.
Well, I wish I could help, but well, let's try my charger. If it works with yours, that should be a good way to test it.
They have an outlet out here too, so that works. The
16 for 8 squared.
I thought we were just finding the 16 squared and
Yeah, and
oh.
I think it works today.
Here, this is a better way to test it. Okay. So you got it in both cases, right? So you're doing this and you're doing 16. What'd you get for your stopping distance at 8? Violet?
106.7.
Good.
It's working.
And then you should have not had to calculate both, right? You know that if we've doubled our speed, the stopping distance is 4-fold. Actually, I stopped right here in the video. I think I stopped right there. I'm not certain, somewhere in there. So you should have gotten 426.7 if we double the speed, okay? So you shouldn't have to actually go through and recalculate. All you need to do is get one, and then you know the other.
What was the 8 meters per second
whatever.
106.7.
Wait, how'd you get that?
We went 120. We 1 half 400, which is 200. 0 minus 8 squared, which is 64. The two negatives cancel, so you get 200 times 64 divided by 120. I have it right here. 200. 200 times 64 divided by 120. This was the equation. We've canceled out our negatives. Now, this is also meant to be a driving lesson for you guys. As you increase your speed, your stopping distance goes up nonlinearly. And if you're around a truck which has 20 times your mass, just think of what that truck stopping distance is. I belabored this point a few years ago, and especially about trucks and pulling out in front of trucks, big trucks. And there was a girl who did very well in the course, and then in the spring, after I'd belabored the point, she pulled out in front of a truck, not giving it enough time. The truck hit her car and basically permanently, I guess, mentally impaired her boyfriend. So, and Glenpool, a girl, 16-year-old, pulled out in front of a truck and was killed. You have to be very careful. Their stopping distance is going up linearly with their mass. They have a bigger brake force, but that could be, it's not at all corresponding. So if they have that enormous cargo, that heavy cargo in there, just think of their stopping distance. You don't want to get anywhere near them. When you pass them, you have to give them a great deal of space. And when you drive, you need to realize as you increase your speed, your stopping distance is going up nonlinearly. You only have so much brake force on your car and no more. Okay. All right. We'll go on break.
I think it's Sean.